On December 14, 1972, a man named Eugene Cernan climbed up a ladder on the surface of the moon, took one last look at his own boot prints in the gray dust, and became the last human being to stand there. He said a few words about coming back, and then nobody did. Not for a year, not for a decade, not for 50 years and counting. The most expensive, most watched, most triumphant journey in human history happened 6 times. And then we simply stopped and let the whole thing gather dust for half a century. And here's the part that should stop you cold. Right now, all at once, everyone is suddenly going back. The United States, China, India, private companies you've heard of and ones you haven't. There are landers crashing and landing on the moon almost every few months now. 2 competing blocks of nations are racing to plant bases at the exact same spot. After 50 years of total silence, the moon is the most crowded destination in spaceflight. So what changed? Why was the moon worthless for 50 years, and then, almost overnight, the most valuable real estate in the solar system? The answer isn't one thing, it's 4. And once you see them, you'll understand that this new moon rush has almost nothing in common with the one your grandparents watched on television. But to understand why we're going back, you have to understand why we left. And the uncomfortable truth is this: Apollo was never really about the moon. Apollo was about beating the Soviet Union. It was the Cold War with rockets. In 1962, John Kennedy stood up and committed America to landing a man on the moon. And the goal, stated plainly in private, was to demonstrate that American technology, and by extension American democracy, was superior to communism. The moon was the scoreboard, not the prize. And it worked spectacularly. But once Neil Armstrong's boot print was on the surface, and the flag was planted, and the world had watched America win, the entire political reason for going evaporated. The science was real, but the science alone was never going to justify the cost. At its peak, the Apollo program consumed something like 4% of the entire U.S. federal budget. 4% of everything a superpower spent, poured into a race that, once won, had no encore. So the budget was cut. The last 3 planned missions were canceled, and the most advanced machine humans had ever built, the Saturn V rocket, was simply retired and put in museums. We didn't leave because we failed. We left because we'd already gotten what we actually came for. And here's a detail that surprises people and explains why we couldn't just casually pop back whenever we felt like it. There's a popular myth that NASA lost the blueprints for the Saturn V. That's not quite true. The plans exist. What was actually lost is harder to recover: the institutional knowledge. The Saturn V had over 3 million parts, and building and flying it depended on thousands of engineers and technicians who carried expertise no document fully captures. The hard-won feel for how to test it, tweak it, and not kill anyone. When the program ended, those people scattered and retired. The specialized factories retooled. The supplier networks dissolved. You cannot rebuild a moonshot by photocopying an old binder. You have to rebuild the entire living ecosystem of people and industry around it. That's a huge part of why returning to the moon wasn't a switch we could simply flip back on. We didn't just stop going. We dismantled the machine that took us and let the people who knew how to run it walk away. Coming back meant building it all again, almost from scratch. And that only makes sense if the reasons are strong enough. For 50 years, they weren't. Now they are. So that's the backdrop. For 50 years, the moon was a place we'd been, a box we'd checked, with no compelling reason to pay the staggering bill to return. Now let's talk about the 4 things that flipped that completely. The first, and maybe the biggest, is that we found something there that changes everything: water. When the Apollo astronauts brought back their moon rocks, the samples looked bone dry. For decades, the textbook said the moon was a dead, desiccated rock. But starting in the late 2000s, a series of missions blew that idea apart. In 2008, India's first lunar probe, Chandrayaan-1, carried a NASA instrument that detected the signature of water molecules across the surface. Then, in 2009, NASA did something wonderfully blunt. It took a spent rocket stage and deliberately crashed it into a permanently shadowed crater at the moon's south pole, then flew a second probe straight through the debris plume to see what got kicked up. That mission, called LCROSS, found water in the plume, and not a trace. It detected around 155 kilograms of water from that single impact. And the deeper they looked, the more there was. The current estimates, based on radar from orbiting spacecraft, suggest the moon's poles hold something on the order of 600 billion kilograms of water ice. Enough, by one comparison, to fill hundreds of thousands of Olympic swimming pools. And that's considered a low-end estimate, limited by how deep our radar can see. This ice is locked in craters near the poles so deep and so permanently shadowed that sunlight has never touched their floors, where temperatures sit at hundreds of degrees below zero. Cold traps that have been hoarding ice, possibly delivered by comets, for billions of years. And this is exactly why everyone is suddenly obsessed with one specific, tiny region, the lunar South Pole. Not the equator, where Apollo landed for easy access, the pole. Because the pole is a geographic miracle. The moon barely tilts on its axis, which creates two opposite extremes sitting right next to each other. Some crater floors near the pole are in permanent darkness, never a single ray of sun, ever, which is why they trap and hold the ice. But just a short distance away, on the high crater rims and peaks, there are spots bathed in almost continuous sunlight, sometimes called peaks of eternal light. Put those two facts together and you have the perfect base site. Near-permanent solar power on the heights to run your machines, and a frozen reservoir of water in the shadows right below to mine. There is nowhere else on the moon, arguably nowhere else nearby in the solar system, that hands you energy and water in the same neighborhood. India's Chandrayaan-3 made the first successful soft landing in that polar region in 2023. Every major player is now aiming for the same narrow band of real estate. As recently as 2026, India's still-orbiting Chandrayaan-2 found fresh radar evidence of ice buried beneath the floors of those polar craters. The hunt is converging on a single address. Now, why does frozen water turn a dead rock into the most valuable property in the solar system? Because in space, water isn't just for drinking, though it's that too. Water is air. Split it apart, and the oxygen is breathable. And most importantly, water is fuel. Break water into hydrogen and oxygen, and you've made two of the most powerful rocket propellants that exist. The trick to do it is almost embarrassingly basic chemistry. Run an electric current through water, electrolysis, the same thing you might have done in a school science class, and it separates into hydrogen and oxygen gas. Power that with solar panels on those sunlit peaks, and the moon base could, in principle, manufacture its own rocket fuel and its own breathable air out of mined ice, using little more than electricity and patience. Think about what that means. The single most expensive, most limiting factor in all of spaceflight is hauling fuel up out of Earth's gravity. Every kilogram of propellant a Mars-bound ship needs has to be dragged up through Earth's powerful gravity well at enormous cost. But the moon's gravity is only about 1/6 of Earth's. Fuel made on the moon can be lifted off it for a tiny fraction of the energy. So the vision is this. A ship launches from Earth carrying just enough to reach the moon, tops off its tanks at a lunar fuel depot fed by mined ice, and then heads for Mars with a full load it never had to drag up from Earth. The moon becomes a gas station in the sky, a place to refuel on the way out to everywhere else. The water wasn't there in the Apollo story. Its discovery rewrote the entire economic logic of the moon. But a valuable destination is useless if you can't afford the trip. Which brings us to the second thing that changed, and it's the quiet revolution underneath all of this. The collapse in the cost of getting to space. Here's a number that explains the entire modern space age. During the space shuttle era, putting 1 kilogram of anything into low Earth orbit cost on the order of $50,000. For decades, across the 1970s through the 2000s, launch costs stayed stubbornly, brutally high. Tens of thousands of dollars per kilogram, because every rocket was thrown away after a single flight. Imagine scrapping a jumbo jet after one trip from New York to London. That was rocketry. And it kept space as the exclusive playground of superpowers. Then reusable rockets arrived. By landing and reflying the first stage of its Falcon 9, now done hundreds of times, SpaceX drove the cost per kilogram to orbit down below $3,000. That's already a reduction of more than 90% from the shuttle. And the next generation Starship, a fully reusable giant, is targeting figures that sound almost fictional, potentially under $100 per kilogram, from 50,000 to maybe 100. When the price of the trip falls by a factor of 100 or more, things that were economically insane suddenly become merely difficult. A moon base was unthinkable, not because we lacked the will, but because we couldn't afford the freight. That math has changed. And falling costs did something else. They let companies, not just governments, into the game. NASA no longer builds everything itself. Through programs that pay private firms to deliver cargo to the lunar surface, a whole industry of commercial moonlanders has sprung up. Some of them have crashed, some have tipped over, but some have worked. And each one costs a fraction of an old government mission. The moon is no longer a place only two superpowers can reach. It's becoming a place a startup can ship a package to. It's worth pausing on how strange and new this is, because the contrast is stark. NASA's own giant moon rocket, the Space Launch System that flies the Artemis missions, costs on the order of $4 billion per launch. A magnificent machine, but built in the old, expendable, thrown away after one flight tradition. Meanwhile, NASA has started simply buying rides, handing relatively small contracts to private companies and saying, in effect, here's our science payload, you figure out how to land it. The first wave of these private landers has been a brutal, very public learning curve. One ran out of fuel and never made it. One came down too hard and broke. One landed but tipped over onto its side, crippling it. And then others have set down successfully and sent back data, something only a handful of governments had ever achieved. Each of these costs a fraction of a flagship mission, which means we can afford to fail, learn, and try again on a timescale that was unimaginable when every attempt cost a national fortune. Failure used to be a catastrophe. Now it's a line item. That shift, being able to treat moon landings as something you iterate on rather than bet the agency on, is itself a quiet reason the moon is suddenly reachable. So the prize got richer and the trip got cheaper. The third thing that changed is that someone new showed up to take it, and that turned a quiet scientific interest into a flat-out race. China. In the time the West spent treating the moon as finished business, China built, from essentially nothing, one of the most methodical lunar programs in history. Its Chang'e missions did things no one had done in decades, landing on the far side of the moon, the side we never see from Earth, and returning samples, including the first samples ever brought back from the moon's far side. And China has stated its goal plainly: land its astronauts on the moon by 2030, and build a permanent base near the South Pole, the International Lunar Research Station, in the years after, with construction targeted through the 2030s. This has reorganized the entire world's space ambitions into something that looks eerily like the old Cold War, but with new players. On one side, the United States leads the Artemis program, which in April of 2026 sent 4 astronauts around the moon on Artemis II, the first crewed lunar voyage in over 50 years, backed by dozens of nations who've signed on to its rules for behaving on the moon. On the other side stands China's program, which has drawn its own coalition of partner nations. 2 blocks, 2 sets of rules, both aiming for the same handful of prime spots at the lunar South Pole, the ones near the water ice and near the rims that catch near constant sunlight for power. And here's the strategic core of it, the thing that makes governments spend billions. It may matter less who profits from the moon's resources, and more who gets there first and sets the precedent for everyone else. Being first isn't about the flag anymore, it's about writing the rules. And neither side wants to live in a future where the other side wrote them. And the race is genuinely close, closer than national pride on either side would like to admit. China is methodically laying its groundwork with robots before risking people. A mission called Chang'e 7, targeted for around 2026, is designed to survey the South Pole's environment and hunt for that water ice directly. And Chang'e 8, around 2028, is meant to actually test using lunar resources on the spot, the first rehearsal of turning moon dirt into something useful. America's side, meanwhile, has been dogged by delays. The first U.S. crewed landing keeps slipping. Problems with the Orion capsule's heat shield, which has to survive the roughly 5,000-degree Fahrenheit inferno of re-entry, pushed the timeline back. And the actual boots-on-the-surface landing has been restructured and moved toward 2028. Look at those dates side by side. China aiming for a crewed landing by 2030, America aiming for the late 2020s. And you realize that for the first time since 1969, there is a real, live possibility that the next person to walk on the moon will not be American. Every delay on one side narrows the gap. That is exactly the kind of pressure that loosens government wallets. Now, before we go further, it's worth being honest about why all of this is so hard. Because staying on the moon is a vastly bigger problem than the few-day Apollo camping trips. And it explains why even with all this momentum, progress looks slow. The moon is trying to kill you in ways that are easy to underestimate. Start with the dust. Lunar regolith isn't soft sand. With no wind or water to ever smooth it, every grain is jagged and razor-edged, and it's electrostatically charged so it clings to everything. Apollo astronauts found it ground through seals, scratched visors, clogged joints, and irritated lungs, and they were only there for days. A long-term base has to solve a dust problem that chews up machinery and is genuinely toxic to breathe. Then there's the night. A lunar day-night cycle lasts about a month, which means roughly 14 Earth days of continuous, frigid darkness, with temperatures crashing far below zero and solar panels going dead the whole time, which is exactly why those permanently sunlit polar peaks are such prized real estate. Add the radiation with no thick atmosphere or magnetic field to shield the surface, and you need serious cover just to survive long-term. The proposed solutions are a big part of why now is even thinkable. Instead of shipping heavy shielding from Earth, engineers plan to build with what's already there, piling regolith over habitats for radiation cover, or even 3D printing structures out of melted moon dirt, layer by layer, with robots that arrive before the humans do. There are also plans for a small space station orbiting the moon, a waypoint called Gateway, to serve as a staging post. None of this existed as a realistic toolkit in the Apollo era. The reason we can talk seriously about living on the moon now, rather than just visiting, is that the technology to use the moon against itself, its own dirt as our shield and our building material, has finally caught up to the ambition. Which leads to the fourth and final reason, the one that reveals this whole thing isn't really about the moon at all. The moon, this time, is a stepping stone. In the Apollo era, the moon was the destination, the whole point. You went, you planted the flag, you came home. This time, almost every serious player describes the moon the same way, as practice and as a launch pad for Mars. The logic is that going straight to Mars, a journey of months where help is impossibly far away, is too big a leap. The moon is 3 days away. If something goes wrong, you can get home. So the moon becomes the proving ground, the place to learn how to build habitats that survive brutal radiation and dust, how to mine local resources and turn them into water and air and fuel, how to keep humans alive on another world for the long term. Master all of that on the moon, 3 days from rescue, and you've built the toolkit for Mars, where there is no rescue. The moon isn't the summit anymore, it's base camp. And there's a longer-term prize whispered in the background, still speculative but tantalizing. The moon's soil is rich in things that are rare on Earth. The most famous is helium-3, an isotope that's almost non-existent on Earth but has rained onto the airless moon from the sun for billions of years, and which could one day be a fuel for fusion reactors, if we ever crack fusion. Whether that ever pays off is a genuine open question. But combine it with the water, the strategic high ground, the stepping stone to Mars, and the sheer prestige, and you start to see why the calculation flipped so hard. And there's one more prize that has nothing to do with money or war. Pure science that you can only get on the moon. The far side, the hemisphere that permanently faces away from Earth, is the quietest place in the entire inner solar system, radio-wise. Earth is screaming with radio noise. Every phone, every broadcast, every satellite. And our atmosphere blocks certain wavelengths entirely. But the bulk of the moon acts as a 2,000-mile-thick shield. Stand on the far side, and Earth's racket is completely blocked. Scientists want to build a radio telescope there. There's a serious NASA-studied concept to drape a wire mesh a kilometer wide across a far-side crater, using robots, to make the largest radio telescope in the solar system. From that silent vantage, we could listen to wavelengths that have never been heard, peering back toward the cosmic dark ages, the era just after the Big Bang, before the first stars switched on. China's far-side landings have already taken the very first baby steps toward this kind of observation. The moon isn't just a fuel depot and a strategic prize. It's also a window onto the early universe that exists nowhere else within reach. So put the four together and the mystery dissolves. Apollo went to win a race, and the moment the race was won, the reason vanished and we left for 50 years. We're going back now because all four things that were missing the first time suddenly exist at once. There's water that turns the moon into a fuel depot. Launch costs have fallen by a factor that makes the impossible affordable. A new superpower has turned interest into a race nobody dares lose, and the whole endeavor has become the rehearsal for Mars. None of those were true in 1972. All of them are true now. Eugene Cernan thought he'd be back in a few years. He died in 2017, having watched half a century pass, with his boot prints still the freshest ones up there, untouched, undisturbed. Because the moon has no wind and no rain to erase them, those prints are still there tonight. But for the first time since he made them, they're about to have company. And this time, the people coming aren't planting a flag and leaving. They're coming to stay.